Hi guys, and today I am going to discuss about the LTspice simulation of Universal Shift Register by using the IC 74HCT194. Okay, so this IC I am going to use, and you know what is the operation of Universal Shift Register. And Universal Shift Register means it is going to do all the operations, namely your shift right, shift left, and your parallel mode. Okay, so that is what will be done by using your Universal Shift Register. And coming to your Universal Shift Register, by using D flip-flop, which I have already discussed the theory in my previous lectures. And here we are going to use 4D flip-flop with the help of a mux, and 0 for shift right, 1 for 0 for no change, 1 for shift right, and 2 for shift left, and 3 for your parallel operation. That is what we are going to do. And with the help of your select lines, whatever data that is being present in 0, 1, 2, 3, that will be transferred to the mux, where the mux will be, output of the mux will be connected to your DA. Output of the mux will be connected to your flip-flop input. Okay, so S0, S1, as I said earlier, you will be having 4 different combinations for your S0, S1, which is nothing but your 0, 0, 0, 1, 1, 0, 1, 1. So S1 being your most significant bit, S0 will be your LSB. So 0, 0, 0, 1, 1, 0, 1, 1. So this is your 4-bit combination, where 0, 0 is your no change, and this is your shift right, this is your shift left, and this is your parallel mode of operation. Okay, so this is what we are going to see here in your shift register. All the 4 modes of operation we are going to do in this shift register, but we are not going to use your DA flip-flop. Instead, we are going to use a separate IC, namely IC 74HCT194. that is an universal shift register. Okay, universal shift register. And we know for your shift right and shift left operations, okay, shift left, whatever data that is being fed, if it is the shift right operation, so you will be feeding the data here, so if it is 0, 1, 0, 1, so we need 4 clock pulses to feed in the data 0, 1, 0, 1, 0, 1. To feed in the data, we need 4 clock pulses, and to receive the output that is being fed 0101 at the output QD, we need another 4 clock pulses. That is what I have discussed. So we need totally 8 clock pulses. Okay, we need totally 8 clock pulses for your shift right and your shift left operation. We need 8 clock pulses. And parallel mode of operation, see, you need a single clock. Within a single clock itself, whatever data that is being fed, because DA, DB, DC, all will be fed, and everything at the same time we will be feeding the input to your flip-flops. So we need only 1 clock pulse for your parallel mode operation. So your mux will decide which modes of operation that the given IC is going to be operated with. So we need to clearly define your timing period, like for which time you are going to use this particular universal shift register as an shift right operation, or as an shift left operation, or for a parallel mode operation. We need to define exactly by using your 74HCT197. So here in this LTspice simulation, what am I going to do is, I am going to take the select line inputs like this. So namely, I already said my S1 and S0, S1 being your MSB and your this is your LSB in case of your mux. Okay, so you have an inbuilt mux in case of your 74HC2194. Only S1 and S0 pins will be projected out, where you will be giving your signals, okay, in terms of zeros and ones. And so this is what we are going to define here. and along with the clock pulse and your inputs. Okay, along with the clock pulse and the inputs. And already I said here for your shift register, and this is going to be your LSB. Okay, and this is going to be your most significant bit. Okay, your most significant bit. That is what usually you think this is LSB and this is MSB usually. Okay, you keep that in mind. So now, so I said we need to define your operation. So how am I going to define my operation is, first let me take shift right operation, being 0, 1 is your shift right operation. Okay, shift right operation. And after doing shift right operation, my IC has to do nothing, meaning no change. Okay, and again I need to go ahead with your shift left operation. Shift left operation with the most significant bit is 1 and 0, shift left. And again after performing the shift left operation, the IC has to do nothing, so no change. Okay, after this, let me go ahead with the parallel mode of operation. Parallel mode of operation is 1 and 1. Okay, this is your parallel mode of operation. So I'm going to define my mux timing line as this. So 0 0 1 0 1 and 1 0 0 0 1. And we have a clock, because whatever clock that we are giving for your shift register, based on the clock only your shift register is going to respond. Okay, so along with the input and with the clock, the rising edge of the clock 74HCT194 is has positive edge triggered clock. Okay, meaning for every positive rise of your clock, whatever may be the input that is being present, that will be moved to your the next stage, or if it's a parallel mode, to the output. Okay, so positive edge triggered clock. So we need to define the clock first, because based on the clock only we are going to take out your response. So clock, how am I taking my clock is, I am taking 1 millisecond on and 1 millisecond off. Okay, so with the total time being 2 milliseconds. Okay, the total time being 2 milliseconds. This is my clock pulse. Okay, this is my clock pulse. So positive edge triggered clock means like during your rising edge of the clock, whatever input that is being present. Okay, so if for my input has to be present before the rising edge of the clock. If it is like that, it will be easy for us to visualize the output. So only if your input is present before your rising edge, we can see easily how your 74HCT responds to your input. So what am I doing is, see for from your rising edge of the clock, for the entire clock cycle, whatever may be your input is, that input will be present in the output. Okay, or that input will be transferred to your shift register. Okay, so now let me take here, so for this entire 2 milliseconds time, so here what am I going to take is, okay, here the input, instead of appearing for 2 milliseconds, let my input will appear for 1.8 milliseconds. Okay, first let it be 0 and then 1, 0 and 1. Okay, so 1.8 millisecond, 1.8 millisecond, 1.8 milliseconds, like that. So if I take this input period, for example, I am telling this is 3.6 milliseconds. Okay, so keep in mind, for both for your shift right and shift left, I am going to take only the input 0, 1, 0, 1. Okay, keeping in mind the 0 and 1, 0, 1, each transition, okay, will occur for 1.8 milliseconds, which is slightly lesser than your clock pulse period. I am taking in such a way that this 1.8 millisecond, this changeover in the input will occur before the rising edge of the clock. before the rising edge of the clock. So I am taking the input 0101 both for my shift right and my shift left operation. Okay. Okay, as I said, for the shift left and the shift right, we need 8 clock pulses for getting our total desired output. Okay, and let us define the timelines here. Okay, only then we will be getting approximately your output here. With respect to input, let me define, because my input has to be ahead of my clock pulse. Okay. So 8 cycles I need, means 8 clock pulse approximately. Let it be, I will take in terms of input itself. So 1.8 into 8. So I need 14.4 milliseconds for getting my total output in terms of, I am telling in terms of input. In terms of clock pulse, I need, so 2 into 8, 16 milliseconds. Okay, the wholeheartedly. So let me take 8 milliseconds for no change according to the clock, and another 16 milliseconds, meaning 40 milliseconds. This is up to 24 I will be having this, up to 16 I will be having this from 0, and up to 40 I will be having this, and again another 8 milliseconds for no change. So up to 48 I will be having this. Let me take 40 plus 16, so 64 milliseconds I will be having this. So till 64, 48 to 64. So for shift right operation, according to the clock pulse, it will be from 0 to 16 milliseconds, and no change from 16.01 milliseconds to 24 ms, and shift left operation 24.01 ms to 40 ms. Again no change will be from 40.1 ms to 48 ms, and again parallel mode of operation from 48.01 ms to 64 ms. Okay, so this is how you will be defining the time in terms of clock pulse. So let me go ahead with respect to my input also. So 14.4 plus 8, so this is up to 22.4 milliseconds I will be having this, and 22.2 plus 14.4 and up to 36. I need to define, I need to reduce by 2 milliseconds, that's all. Up to 36.8 I will be having this, plus 8, 44.8 I will be having this, and then plus 14.4 up to 59.2 I will be having this, because 1.8 into 8, right, that is 4.4. Up to 59.2 I will be having this. In terms of input, I can even define this. Okay. So let me define this in LTspice. So let me take this waveform. Let me take this voltage pulse for defining all these signals. So I need 3 inputs, shift left, shift right in parallel mode. Okay, and then I need 2 for mux and 1 for my clock pulse. Okay, and then let me ground this first all, and let me name this by using label net. Okay, take as an input first shift right. Okay, I'll be giving this to all. Later I'll change the name. So now that I have defined all, okay, so shift right, shift left, parallel mode, everything. Okay, so let me define my S0, S1 first. Okay, go ahead with the advanced. Don't go for the pulse, go for pulse definition. Okay, so see here we have defined like till 14.4 we will be having our S1 as we have up to till 22, right? Till 22 milliseconds we have 0 only for S1. Okay, so this is for S1 till 22 milliseconds it is 0 only. Okay, it is 0 only. So from 22.01 milliseconds it is going to be 5. Till when? Till it is 36.8 milliseconds. Okay, so 36.8 milliseconds I will be having 5. So from 36.801 ms I will be having 0. Go ahead with the additional points because we need some more points to be defined. So, and up to 44.8 it is 0. ms it is 0. Till when? Till 59.2. 59.2 milliseconds. This is going to be 0 only. Okay, for the next 8 milliseconds let me take 59.2 plus 8. Okay, 67.2. Let me take approximately I am taking. So I have defined this period. See here. So first 22 milliseconds it is 0, and then later from 22.01 till 36.8 it is 5. After that from 36 till 59.2 it is 0 only. So I have defined intermittently also, that's 47 0.8 also 0. So I can even delete this. Till 59.2 it will be 0 only. Okay. From 36 till 59 it is 0. From 59 point till the next 14.4 milliseconds, that 8 clock pulses, I took it for the parallel mode of operation. This is for S1. Okay, I have defined for S1. Is it okay? So 20, 10, 1. So till 22, 101. Let me go ahead with S1 again. The same way, let me define. So I have defined this S0 and S1 accordingly as given by the data by using your pulse. Okay. So see, for S0 also I have given. Okay, S1 also I have given. Look here, I have taken like this. So till 22 milliseconds my S1 is 0, and from 22.401 till 36 it is 1. From 36.801 till 44.8 it is 0, and 44.801 till 59.2 it is 1 for parallel mode of operation. Okay. Similarly, I have to define for my S0 also. That is what I have done here. So till 22 milliseconds it is 0. From 22 to 36 it is 5. 36.801 it is 0. Okay. Till 44.8 it is 0. And 45.801 it is going to be 5. Till 59.1 it is going to be 5. Okay. This is the exact S0 and S1. Okay. Clock pulse, normal pulse we can go ahead. So advanced, go ahead with your normal pulse. So 0, 5 and 0 delay, 1 nano, 1 nano, 1 milli, 2 milli. Okay, that is your normal pulse. So let it be here itself. And shift right and shift left you need to define. So again we need to define. Go ahead with your shift right pulse definition. So I am give the data 0 only. So 0, 1, 0, 1 like that. So for first 1.8 milliseconds it is going to be 0, and from 1.801 it is going to be 5 till 3.6 milliseconds it is going to be 5. Okay. So 3.601 ms till it is going to be 0, and so up to 5.4 milliseconds it is going to be 0, and 5.401 ms it is going to be 5 again, and till the 7.2 ms this is going to be 5 again. Okay. After that let it be 0, meaning from 7.201 ms, because we don't want this shift left, shift right input. After that let it be 0. Okay. Okay. Click OK. Okay. Let it be, pull this up and keep it here. Go ahead with your shift left again. Go ahead with your pulse, and where you have your shift left operation from 22.4. Okay. So till 22.4 ms it is 0. So I'll take another 1.8. So 24.2 milliseconds. It will be 0 only. And 24.201 ms. It is going to be 5. Till 26 ms. It is going to be 5. 26.20 01 ms. It is going to be 0. And 27.8 ms. It is going to be 5. So 0 1 0. It is going to be 0 only. Then 27.81 ms. It is going to be 5 again. Till 29.6 ms. It is going to be 5. And 29.61 ms. I no longer need this input, so I will make this 0. I have defined this also. You pick it and place it here. Okay. So this is for my shift left operation. And parallel mode of operation, input has to appear from 48.8. Okay. So 48.8 it has to appear. So parallel mode of operation, let it be a normal pulse itself. And I will take a delay 0.5, a delay of 48 point or even 49 ms, 1 nano. It will be 4 ms and 8 ms on time and off time. So this is for my parallel mode. Okay. And then for visualizing my output easily, let me take an OR gate. Digital or click OK, paste it here and go ahead with the label net. So look here, I have taken my shift left, shift right and parallel mode of operation to visualize my in an OR gate, to visualize it easily. Okay, let me first visualize whether these signals given or appropriate. Then we will take this 74HCT194 and then simulate. Okay. So look here, what we have done here. First is 0 1. So this is my shift right input, and then after that we are going to do nothing. Both are 0 0. Multiplexer output 0 0, and then 1 0. This is for shift left. Am I right? See, 1 0 is shift left, 0 1 is shift right, and then later again we are going to give some blank space, which is nothing but no change state, and 4 milliseconds on, 4 milliseconds off indefinitely, and this is our parallel mode of operation. So now whatever the signal description is right, let us work with the 74HCT194. What I am going to do, I am going to take a IC 74HCT194. Okay, so I am going to place it here. Extreme right is okay. I'll just shrink it down slightly. Okay. right. So now this MR input, okay, it's an active low input signal. So that has to be high according to the pin definition. I'll show you here. So this is our 74HCT194's data sheet. So MR has to be low for clearing all the input, okay, for clearing all the input, and later if only if it is high, it will do all the other operations, namely hold, shift left, shift right, and parallel. Okay, so data shift and data shift right, shift left, the data has to be given. So S0 and S1 accordingly I have chosen. These are the 4 outputs. Okay, 4 outputs. So see here, clock has to be high. So it is an positive edge triggered flip-flop. Okay, clock has to be high. CP is the clock pulse. Is it okay? Right. So let me take one more voltage input. Place it here. I have defined this as a pulse itself for first 59.2 milliseconds up to this period till all the parallel mode of operation to be over. This has to be in high. Okay, that is why I have given a delay of 59.2, and later it has to be 0. Okay, sorry, without delay I have to give 0, 5, first 59.2 it has to be high, and later it has to be 0. Okay, later it has to be 0. So now I have given my input here. Let me use label net itself here. So S0, it will be my input. So S0 is right. S0 clock pulse, shift right. I can even connect all this again. Okay, I'll give it here itself. This is going to be my shift left. This is going to be my shift right. So I have defined MR here, S0, S1, clock pulse, shift right input and parallel mode input, and your S0, because all the 4 bits I am giving the same data. For example, if it is 1 means all 1 and 0 means all will be transformed to 0. And Q0, Q1, Q2, Q3, it is here. Okay, label net here. Okay, go for edit spice analysis. Let me go ahead for 66 milliseconds because I need to see the reset also. Okay, so let me run. Already I have given this. Instead of S0, let me take this as add traces, my MR input. Okay, and then add plot plane again, because we need to see the output also, right? I have shifted this, and then I am going to add the traces Q0, Q1 parallelly. So this is my output I am getting. Shift right is behaving properly, 0, 1, 0, 1, but not my shift left. So I think the time is not proper. This input has to appear here before this, meaning at this point around 21. So let me change my input. Okay, shift left input time. Let me shift it, then it will be right. Okay. Guys, I have adjusted the timelines of S0, S1 again, and such that my change in the input, namely my input again, so 0 1 0 1 is my input for my shift right. Okay, so 0 1 0 1 0 1 is my this input for my shift left, and I am giving a blank space, I am not giving any input here, and then this is my parallel operation. And mode input, as I said, for some time I am going to give this low because I need to reset it. Okay. So let it be 0 1 shift right. So I need to see from the Q0 because that is going to be your LSB. This is going to be the Q0. So from left to right. Okay. And this is by Q3. So for shift left operation I have to see. Shift right I need to go ahead with this Q0. So shift right. So from Q0. So this is the same input 0 1 0 1. This is going to appear here. Shift it here. One time space. So 0 1 0 1 0 1 0 1 0 1 0 1. Till then your all the other Q1, Q2, Q3 will be 0 only, because the first output only when it is fed to the second, and your clock pulse should also be high. Your clock pulse should also be high, only then your next flip flop will respond. That and all you know according to your shift register. And for your shift left I have to see from here, it is 0 1 0 1. So 1 bit shift 0 1 0 1, and again here 0 1 0 1, and here 0 1 0 1. And this is my parallel operation input. It will appear at the same time. I am going to give all 1 at a time, all 0 at a time, all 1 at a time, all 0 at a time. Okay, see, but this is not appearing because my MR input is low here. So from this point of time, okay, from this point of time, this will be entirely 0. From this point of time, okay, entirely 0. That can be very well defined if I change this parallel mode with a delay. So parallel mode of operation, parallel mode of operation. I am giving a delay, right? Okay, let it be like this itself. Okay, so from this point it will be 0, all 0 as a parallel mode operation, and this is resetted after that. Okay, this is after that resetted. I took spice analysis, edit, spice analysis, and in your transient 65 milliseconds, and I have run this. This is my output I am getting. Okay, I adjusted the time frame. I have adjusted the time frame for you to be visualized properly. Let me zoom and bring this in. This is my S0 S1. This is my shift left, shift right, and this is for my CP and PM, parallel mode operation clock pulse, and this is going to be your 74HCT194 and your MRI transient. Okay. This is going to be entirely defined. Okay. Thank you guys.